Okay, so I'm going to try something a little bit new. Since we have so many people out for quarantine, I'm actually going to try just recording what I would usually do. And I guess I don't need this because it's after school and I'm the only one here. So please get on Google Classroom and click on the link for the document Real World Mathematics. If you need to, you can pause this video and come back to it. But I'm going to go and get started. So this has been something I've been working on for a long time. I really think that there are some good examples I can show you guys for what might come up in your adult lives. And I say the real world, I realize that school for you right now is the real world. So please don't take any offense to that. All right, so the very first part of your packet for today is asking for a scenario. So your little bell ringer today, it's going to be a scenario that's asking you to go back in time and to help out this hunter-gatherer group with some tools. So if you would, go ahead and pause, think through the question, write it down if you want to write it down, and then come back. Okay, so the question basically was saying you're going back in time and you're working with hunter-gatherers and they're just starting to plant crops, but the problem is they're really bad at it. So they don't have any sense of seasons, right? So we actually saw that this happened back in time. So mankind transitioned from being hunter-gatherers into agriculture. And one of the great things that allowed that to happen was actually the development of being able to keep track of days. Things like Stonehenge is a very interesting way that people kept track of days. And if you think about it, Stonehenge just relies on a shadow as the Earth goes around the sun over the course of a year. And based off of where the shadow's hitting on Stonehenge, it's the season. So no math required. So why do we need math nowadays? Well, they created this massive thing for Stonehenge. Nowadays, I can click a single button on my computer and it's going to label every single day, and we put numerical values to it. So if I was going back in time and I was trying to help somebody to figure out seasons, we need some way to keep track of that. So one of the earliest things that we see is just tallies, where people are keeping track by 1 day, 2 day, 3 day, 4 day, and they're just making a notch per day. And eventually we get to a point where we start seeing 5, and we see base 10 systems. You might wonder, why do I see 10 everywhere? Why is 10 what mankind's deciding? And we believe that base 10 really comes from this. We have 10 fingers. And so we honestly believe that a lot of that history comes from 10 digits. So if I was going back in time and I was helping a civilization try to keep track of days, I'd probably suggest some sort of tally mark. As we go throughout history, we see tally marks become a very popular way to keep track of time. So as you go into a little bit later in time, people start trading with one another. And the way that they count up and keep track of those trades is by having a stick. And they cut grooves on that stick. And then they break the stick in two. One person gets half the stick, the other person gets the other half of the stick. And in case there's ever a quarrel about was it fair or not, well, these two sticks would be combined, and if they both showed the exact same thing on both the sticks, then it was obvious that somebody had agreed to this and there should be no quarrel. All right, so just kind of a way for you to think back in time a little bit. And I want you to view math as something that's grown, something that is a technology. We think of technology, and I've got a cell phone here that I can do just about anything I want to with it. But really, mathematics is a technology, and today that technology is in binary, zeros and ones. All right, so let's go ahead and get started on the lesson for today. So it says you are given a choice, and I'm sorry, we should be down on the next page here. It says you're given a choice. I'll give you $5 every day. So I'm going to take out of my wallet, and I say I'm going to give you one or two options. I'm going to give you $5 a day. No 5, just 20. All right, I'm going to give you $5 a day for 2 weeks. Or I'll give you 1 penny, I'll put it in a jar. And at the end of every single day, I will double whatever amount is in the jar. And my question to you is, which one is the better deal? Well, if you would, pause the video for a minute, and try to figure this out. For day one, where it says doubled every day, you should have 0.01 for where you're ending up that day with a penny. The next day should be 0.02. Next day after that, you're going to be doubling again, 0.04, doubling again, 0.08. Keep doubling it. On the other side, you're adding $5 a day, so 5, 10, 15, 20 each day. So go ahead and pause the video, see if you can fill that out, see which one's the better deal. Okay, so you probably should have figured out that the doubled every day is actually better. And there's a term for the kind of growth that we see in both of these functions. So on the first function, that's linear. And you guys are used to linear. I mean, linear growth, you've been doing since 8th grade. That's that y equals mx plus b equation. And if I graph it, it's something like this. All right, it is a straight line, linear meaning line. It's going to go up at a steady pace. Now, the interesting thing about the other side of it, where we're doubling that penny every day, is it's a different kind of equation. And we've been working on that this year. You guys might recognize y equals x squared. This is a different kind of equation. This is an exponential. There's an exponent here. And so exponential growth is going to look something more like this. Okay? And you guys might recognize this is actually half of a parabola. So we have these two different kinds of growth, linear and exponential. Linear is much easier to calculate. That's middle school mathematics. Exponential growth, that's a better technology than linear. That is going to be what we learn in high school, especially as you go into more Algebra 2. And so it's saying which one's which. Well, I think that you could probably figure out that the one that's going up by a constant amount, that $5 a day, that's the linear. The one that's going up doubling, that's going to be your exponential. All right, so if we had to create an equation for each of these, for $5 a day, all right, you're using the linear equation y equals mx plus b. In this case, there's no plus b that you have to worry about. All right, so the only thing you have to worry about is this 5. So what number could I put in there to make an equation for me giving you $5 a day? So I'm going to give you just a second, see if you can figure out what number it needs to be where m is at. All right, hopefully you figure out it's supposed to be 5. All right, I'm going to give you $5 a day. 5 should be the number that's here. As each day goes past, 5 times 1, you're going to get 5. 5 times 2, you'll get 10. 5 times 3, you'll get 15, so on and so forth. The little bit trickier one is the one that's exponential growth. And for exponential growth of the doubled every day, there's a new formula that I'm going to introduce you to. And so the formula for exponential growth is actually total cost. So we're going to look at total of something equals the initial, so whatever the initial value is, in this case you started with 0, so it's an initial value 0, and then we're going to multiply that by 1 plus the growth, and then we're going to take that to the exponent of time. All right, so we have total equals initial, and then inside parentheses 1 plus growth times time. And I know we haven't done this kind of thing before, so let me go ahead and walk you through this. So if I'm trying to make an equation for us doubling a penny every day, well, I still need to figure out the total, so I don't know what that is. My initial value in this case, I'm starting out with a penny on day 1, all right? So I'm starting out with 0.01, all right? And then from there, I need 1 plus my growth. Well, in this case, my growth is being doubled, all right? Or I'm growing by 100% every single day. Well, 100% as a number is going to be 1. And so if I'm raising that to an exponent of time, in this case, my time is just going to be x, because I don't know exactly how long that's going to be going on for. Now, for this particular equation, my time is going to be 14 days. So you could plug this into a calculator. And 1 plus 1, simplify that, you're going to get 2. All right, now if I go ahead and raise this to the power of 14, all right, that's going to give me some big number, and then I'm going to multiply that by 0.01. And you'll find that after 14 days, you got $163.84. All right? And so this is the equation for exponential growth. And in the real world, we see exponential growth a lot more often than we see linear growth. So Moore's law, for instance, which is this idea that for computers, the number of transistors that are on a circuit or on a processor are going to double every 2 years. Population increase is going to be another exponential growth, because if you think about it, 2 people have a kid, okay, now there's 3 people, right? Eventually 3 people are going to make more kids, more kids, more kids. It's not linear, it's exponential, right? It's going to keep going up as the population keeps doubling, or by whatever amount it goes up. You have exponential decay when we talk about the half-life of an element. You start with this big element, and then after X amount of time, you have half that element, then it halves again, then it halves again, then it halves again, all right? That's going down by half. It's exponential loss. Another one that's very common in classrooms, projector light intensity, will be something that is exponential. So if you think about a light, if I am half as far away, it's actually going to be 4 times as bright. So if I took my projector and I moved it back twice as far as it is, it'd be 1/4 as bright, because it's exponential. A very interesting one right now, and exponential growth, is virus spread. And there's a really neat formula that you can look up for the spread of COVID, and they call the R value of how quickly COVID's going to spread. And then the one that we'll get into today is also investment growth. So certain places where you can put your money, and it's going to grow like this. It's the reason why those that are wealthy can get very wealthy very quickly. Think of Elon Musk, Bill Gates. They become much wealthier at a much faster rate than any of us because of exponential growth. And if we know exponential growth, then we can use it to our advantage. And so I'm going to be breaking down a few adult world problems. I'm going to have 5 different problems today, and all of them are based off exponential growth. So you guys have asked me to give you real world scenarios. Well, here are some real world scenarios. So scenario number 1. All right. You guys know I can't draw, so here's a car. All right. So we're just going to say that this is a Jeep, because I can't draw to save my life. All right. So you've got a car, and you go to a car dealership, and you see the car of your dreams, and man, I want to buy that car. But it's $35,000. Now, you don't have $35,000 in your account, so unfortunately you can't pay cash for it. So the car dealership will say, whoa, don't worry, you can still buy the car, but we're just going to go ahead and loan you the money with some interest. And so if you look at adult problem number 1, it's going to lay out a couple of things for this loan. The first thing it's going to lay out is that they're going to loan you $35,000. Then they're going to say, well, you can pay it back over 6 years. So that gives us amount of time. And we're just charge you 5.27% interest. So they say, we're going to be nice, it's 5.27% interest. Really nothing to have to worry about. Don't think too much about it, sign on the dotted line. Well, the question then is, if they're charging you 5.27% interest for 6 years on $35,000, how much are you really paying? Well, you'll see on your sheet that there's the equation, and it's total cost. So total cost equals initial cost. And then we've got, inside the parentheses, 1 plus growth times time. All right, so we've got this equation for exponential growth, and this is one of the greatest equations that you can learn in your life, especially as we get into some later parts of this lesson. I'm going to show you why that's so important. So we want to know the total cost. We don't know that yet. So let's go and set this up. So I know the initial cost is $35,000. That's how much they're loaning me. All right, and then I've got 1 plus growth. Now, growth is just another word for interest, and it's growing by 5.27%. Well, you don't want to put 5.27 in here because this is a percent. So we need to turn that into a decimal. If you don't remember how to do that, you can type into Google 5.27% to decimal. But you're going to remember that 100% equals 1, basically. And so 5.27% is 0.0527 as a decimal. Okay, so 0.0527 would be 5.27%. Now there's one more part of this equation, and that's time. And so I'm just going to go ahead and put in my time, and it says this is for 6 years, so we're going to put that in right here. All right, so my total cost can be found by solving this equation. First thing you need to do is add what's inside the parentheses, raise it to the exponent, then multiply it. I'm going to give you guys a minute. Please pause your video, give this a shot. Okay, so hopefully the first thing you did was you went ahead and added what's inside the parentheses. So we have 1.0527, and then I'm going to raise that to the power of 6. And I need to multiply that times 35,000. And I get a total of $47,632. Wait a minute. What's wrong with this? They were charging me $35,000 that they're loaning me, and there's 5.27% interest. How did that come out to $47,632? That's compound interest. Compound interest is another word for exponential growth. All right. So one of the most dangerous things you can do in your life is sign away any sort of document where you are paying for something long term. This company, the only reason they're doing this is so they can make money. All right. This is how they make all their money. So be absolutely sure before you go signing anything where you are going to be paying something, a contract over a long period of time, that you do the real math. Because I don't know about you, but I'm not paying $48,000 for a car. All right? I'd rather save up $5,000, buy a jalopy that I can drive to and from work, and then continue to save up until I get my dream car. And I can save up $35,000 a lot faster than I can save up $47,000. All right. So in the long run, it's always going to be better not to sign these kind of contracts. You're going to find. All right. So there's our first example. I also have on that problem some of the real-world facts. The real-world facts about buying new cars. That average interest rate, those average years, that is the national average. I use those exact numbers. And $35,000 is the 2021 average price of a new car. Comes out to $568 a month, in case you're wondering. So I'm going to highly recommend don't sign a new car contract. The other thing about new cars, they're going to drop in value as soon as you buy them. They drop by about 30% over 1 year. It's just not worth it. All right, Mr. Cover your life advice. Example problem number 2. So this one's a pretty real world one for you guys here in the next few years. So we talked about cars, and that's a pretty big expense, but there's an even bigger expense that you guys are about to face. And that is going to be, as you probably guess, going to college. Some of you are going to college, some of you might decide not to, but either way, it's smart to understand the math behind it. So if I'm going to college, there you go, there's my little graduation cap. A lot of students just think that they want to take out student loans. So in example problem number 2, it says you get accepted to the University of Tennessee. You're an in-state student, so that means that you're going to pay less than you would if you were out of state. And in case you're wondering, if you're in-state, you'll pay about half of the tuition that you'd be paying out of state. All right, so you're offered a student loan, and they're going to charge you $33,000. Right, they say 1 year of school is going to be $33,000. Well, you don't have $33,000, so they say, don't worry about it, take out a loan. All right. Well, the average that UT is going to charge on that loan is 5.8% interest for 10 years. All right, and here's the problem. Most students, they look at this 10 years and go, oh, that's 10 years away, I don't have to worry about it. I can tell you guys, I'm more than 10 years out of college now. This is something to worry about. All right? This is why people my age are broke. Now, we'll talk at the end of this problem about some different options that you have, but let's go ahead and figure out what this would come out to. All right, so I've got that equation. So I've got total cost equals initial cost. So my initial cost that they're charging me is $33,000 times 1 plus the growth. Remember, the growth is going to be the same thing as the interest. This is 5.8%, so that would be 0.058. And we're going to raise that to the number of years, which is going to be 10. So if you would, go ahead, pause the video, plug this equation into Google or calculator, see what you get out. What is my total cost over 10 years of this loan? Okay, so if I plug this into a calculator, first thing I need to do is simplify what's underneath the parentheses. So I have 1.058. I'm going to raise that to the power of 10 because there's 10 years. And then I'm going to multiply that by 33,000. And I get a total cost of $57,992. Okay. Here's the problem with taking out college loans. They're for very, very long amounts of time. And the problem is, over 10 years at 5.8% interest, you're racking up a lot of money. This is almost double what they initially are telling you they're going to charge. And mind you, this is for 1 year of college. So what do? Some of us want to go to college. I went to college. I can't afford this. So what options do you have? Well, the smartest option is going to be not to take out a student loan. All right? Get a job, work your way through. And I know what you're saying, Mr. Covey, I can't make $33,000 a year. There's no way while trying to go to school. And you're probably right. Well, this $33,000 number includes tuition, books, and room and board. And when you hear room and board, that means your living and your food expenses. Well, if you can stay at home, and I know that's not a fun thing to do, but if you can stay at home, that's going to cut this number down to about $15,000 to $16,000 and becomes way more affordable. Even better, in the state of Tennessee, you get 2 years of community college for free. Go over to Pellissippi for 2 years and get those core subjects out of the way. Those are going to let you transfer directly into any university that you want for your junior and senior year, and it's going to cost you way less than this. I believe over at Pellissippi, you're paying closer to $8,000 a year worth of tuition. All right, so be very, very careful where you decide to go. The other issue with this is the in-state price. For out-of-state tuition, it's almost double. If you want to make a smart decision for college, the number one most important college decision is school choice, and you want to stay in-state, especially when you're in Tennessee, when you get 2 years of community college for free. All right, there's no reason not to take that up. All right, so hopefully this has been a little bit eye-opening to you guys. We've got a couple more problems, and as a heads up on this one, by the way, I took the average. This is the true UT average per year. This is the true interest rate across the country for schools, and this is the average amount of loans. So these are all real numbers. All right, adult problem number 3. This is one that gets people of all ages in trouble, and that's credit cards. All right, so that's not a good credit card. Let's try this again. Warned you guys my drawing skills. There you go. There's my credit card. All right, and a lot of adults think that they have to have credit cards to survive, and we'll talk a little bit about that and what that looks like. But remember, a credit card is just another name for a loan. You basically are allowing somebody to give you money. They're going to charge you interest. And if you mess up and you forget to pay that bill, that interest goes real high real quick. So let's look at problem number 3. And it says you're offered a credit card shortly after graduating high school, which you will be. You paid off quite a few different expenses on it, and unfortunately you racked up $6,270 in debt on it. All right, so we have an initial value of $6,270. Now, your credit card company has told you as long as you make the minimum payments of $93.37 per month, you don't have to worry about them coming after you. And the question is, how long is it going to take you to pay off that credit card if they charge you 17.87% interest? All right, so they're going to charge you 17.87% interest. Now, I know this looks a lot higher than what the other ones were saying, and that's exactly why credit card companies are able to make so much money. This is exponential growth, all right? So you have to be really, really careful with these. Now, if we want to know how long, well, they said that I'm going to have to pay $93.37 per month. All right, that's how much I'm going to have to pay them to keep them happy. So I'm losing almost $100 a month. Well, if we wanted to, we could actually go to our website, and it's linked on your worksheet there. Click on that investor.gov. And then I want you to fill out a couple of things. I want you up at the top to put in this 6270. So under initial investment, it's got a little red asterisk. Go and put in 6270. Where it says monthly contribution, that's going to be how much you pay per month. I want you to put negative 93.37. Length and time of years, we don't have that up here. Just go and put 3 years for now. Estimated interest rate, go ahead and put that 17.87% and go and just type it in 17.87. And then where it says compound frequency, go ahead and put in monthly because you're paying this monthly, and then calculate. Now, you're going to notice that it's going to come up and it's got a graph. But the problem with that graph is it stays flat. Why is that staying flat? So I'm paying money on it, but it's still saying I owe $6,270 a year from now, 2 years from now, 3 years from now, 4 years from now. Why might that be? Well, let's do a little bit of math and find out. The minimum charge that they're charging me is $93.37. Let's see if we can figure out where they got that from. All right, so let's take $6,270 and let's multiply that by our 17.87%. So $6,270 times 0.1787% comes out to $1,120.45. All right, so that's how much they're charging me in just interest. That's not me paying this off. That's how much they're charging me in interest every single year. Okay, well, if I take that 1,120.45 and divide it by 12, I get $93.37, the minimum amount that they're wanting me to pay. So what's happening there? Well, that's what happens with a lot of credit card companies is the minimum payment they make you pay is only for the interest. So this principal is never going down. So if this principal is not going down, you're paying this for the rest of your life. You have to pay more than this value to get this number to actually go down. All right. Better yet, don't ever get in this position in the first place. If you have a credit card, don't ever, ever, ever let it get to the point where you're getting interest on it. There's a reason why the biggest buildings in every single city are credit card or bank companies. In Knoxville, the two biggest buildings, both of them are banks, and they run credit cards. All right. Now, just a quick hit on myths of credit cards. I will tell you, there are certain situations you have to have a credit card. And it gets a little bit tough if you want to rent a car, if you want to get an apartment. Technically, you can do those two things without a credit card, but it gets tricky. You'll notice something. I don't have a credit card. Mine down here says debit. So I actually have gone my entire life without a credit card. I have owned multiple companies. I have never had a credit card. It is possible to do it, but it is trickier. You have to have a debit card. So you will have to have a bank account, you will have to have a debit card, but the difference between a debit card and a credit card is debit card will only let you take out what you have in your account. I cannot take out any additional money that I don't have. Remember, I told you a credit card is then basically loaning you money. This is really, really dangerous. And a lot of people say, well, I'm getting 2% back on my credit card. Well, that's all well and good until that 1 month that you mess up, this interest hits, and all of a sudden you're stuck in this. My best recommendation to you, stay away from credit cards as best you can. All right. It's an adult choice. When you get there, the choice is yours. I'm not saying that they're evil. There are reasons for them, but realize that a credit card is debt. So the reason why it's so dangerous is because of what you're learning in math today. It's exponential growth. All right. It's not like this. All right. This is not linear growth. When you have a credit card, the way that they charge you is exponential. Okay. Get off my soapbox there a little bit. We have one more situation to go over. You'll notice all three of these have been about loans. They've all been the negative side. It's all been about how people are going to try to take money away from you. Well, I've got one good one. We're going to talk about investing. And I'm not going to go too deep into it because I realize that you guys are just kind of getting to that age where you're starting to understand a little bit of it. But let's talk for a minute about investing money. All right? And really, when I say investing, I'm talking about you're putting money away so that when you decide to retire or you want to save up for a car or a house, you have money there. All right. So if we go to our worksheet and you go down to problem number 4, adult problem number 4, it says after graduating college, you get hired making $42,000 a year for a local company. You're 22 years old and you have a dream to retire once you've saved up $1 million. All right, so you want to save up $1 million. That's a 1 followed by 6 zeros. The problem says you're going to put $525 into a bank account every month. So every month I'm going to add $525 into that bank account. All right. How long would it take you to save up $1 million if you're putting $525 into an account every month? All right, I want you guys to pause the video, take a second, and it's going to be a really quick calculation. You're going to take 1 million, divide it by 525, that's going to tell you how many months it's going to take. So go ahead, pause the video, see if you can figure that out. Okay, let's go ahead and do the math. 1 million. That's a lot of zeros. There's 6 zeros there. Divided by 525. Whew, that is 1,905 months. Okay, that's a long time. Let's go ahead and divide that by 12 because there's 12 months in a year. Figure out how many years that is. Well, that's approximately 159 years. Man. Well, I guess we're never going to be millionaires. And the answer here is you're not if you're only putting money into a bank account. All right, bank accounts aren't going to give you any return on your investment. You're just socking money away. It's basically the same thing as putting it, underneath a mattress. Yes, your money will be there. There's no risk. It will stay there, but you're not actually growing any money. All right, so that's problem number 4. Let's go ahead and look at problem number 5 real quick. So problem number 5, it says, same as the above problem, except for in this case, you put that $525 a month into a 401k retirement account. You get 10% interest on your money every year. How long does it take you to save $1 million? Okay. Well, we could go ahead and figure out the math. If we wanted to, we could put it into the exponential formula. In our exponential formula, the total cost, so that's the left side of the equation, we're looking for 1 million. My initial value, I'm not really starting with any initial money, but let's say that, let's say I'm going to start with $1,000. Well, I've got a problem here. This is an initial value. This isn't per month. So how am I going to figure this out if it's per month? Well, this isn't going to work. We're going to have to use a little bit more powerful calculator. Technically, there's math that we could do here. But instead, let's go ahead and make this a little bit easier on ourselves and just use that investor.gov calculator again. So you'll notice that in the problem, there's a link to that www.investor.gov. Go ahead and click on that, and it's going to bring up that calculator. So up at the top of the calculator, it's going to say, what's your initial investment? I want you guys to put 0. Under monthly contribution, we said that we're going to be putting away $525 a month. So go ahead and put $525 into that monthly contribution. Length in time in years. Let's just go ahead and put 40 years. All right. I don't know where that's going to end up. Let's go and put 40. Where it says estimated interest rate. Well, now we're on the plus side of things. We're actually saving money. We're not having other people taking it from us. So our estimated rate is going to be 10%. So just go ahead and put in 10 there. In this calculator, you don't have to put in 0.1. You actually put in 10. And then under compound frequency, go ahead and put monthly and hit calculate. All right. And you're going to notice that it's going to pull up a graph. And on that graph is a whole bunch of different data points. All right, so I'm calculating it here as well. So on that graph, as I go down here, oh, I need to put initial investment as 0. There we go. Not calculating for me. On this graph, you'll notice that you've got some blue dots and you've got some red dots. So the blue dots are how much you're contributing. That red dot is how much this is worth. So if you look at these red dots, you'll actually notice that in year 28, it's almost $1 million. In year 29, it's $1.4 million. In year 30, it's over $2 million. Well, why was putting money into an investment fund so much bigger than just putting in a bank account? Well, it's because of exponential growth. And we started this conversation talking about how those that are wealthy seem to grow wealth at an exorbitant rate. This is why. It's because of exponential growth. It's because of this. You'll notice as I go up in time, year 1, it's up a little bit. Year 2, up a little bit more. Year 3, up more. 4, more. 5. Oh, by year 6, this is huge growth. And that's what exponential growth is. All right. So let's go ahead and do a real-world example of this. All right. And this isn't going to be found anywhere on your sheet. But I'm going to give you a couple of numbers, and you can either plug this into the calculator, or if you'd like, you can put it into the formula and work it out. I'd recommend that you try working it out. So our formula is total equals initial times 1 plus growth, and that's all to the exponent of time in years. Okay. Well, let's say that my initial amount of money that I am putting into this account, let's just go ahead and say that that's $18,500. Okay, so $18,500. Let's say that my growth is 10%. All right, so 0.1. Now let's say my time, let's just go ahead and say 33 years. All right, so the idea is I'm putting $18,500 into an investment, and then I'm not touching it. In this case, I'm not going to add to it ever again. I'm just putting $18,500 into a retirement account. It's growing at 10% every year, and I'm not going to touch it for 33 years. Well, let's go ahead and plug this in, see what we get. I'm going to give you guys just a second here. Try plugging it in. Go and pause the video, see what you come out with. Okay. So if I go and add what's inside the parentheses, that's 1 plus 0.1, so I get 1.1. And let's raise that to the power of 33. And let's go ahead and multiply that by 18,500. Well, let's see. Total amount that I got there was $429,665. That is without adding an extra dime to that money. That is I put $18,500 into an account today. I haven't touched it for 33 years, and it's gone up by 10% per year. In 33 years from now, when I go to take that money out, all of a sudden I have almost $500,000. This is the power of wealth management. This is the power of staying out of debt, of investing wisely. By the way, the average growth for the stock market since its inception has been roughly 10%. So this is a real world number. You also notice something else about some of these numbers. 33, well, if you had 33 to 32, 32 is my current age, that's the age at which I retire, which is 65. It's 18,500. That's how much money I have in my retirement account right now, literally. So if I don't add another dime to my retirement account, I will have almost $500,000 when I retire, just in that account alone, without adding an extra penny. This is the importance of learning these things. The most common question that I get asked as a math teacher is, Mr. Covey, when am I going to ever use this in the real world? Exponential growth is the real world. Right? We went from cars to education to credit cards, now to wealth building. This is how the world speaks. Mathematics, I told you, is a technology. Well, it's the technology that we speak in. It's a language. And the language for us that learn it is success. Out of the top 5 richest people at retirement by jobs, it's not doctors. All right? Top 5, accountants, engineers, teachers are in the top 5. And it's because, honestly, I believe some of them understand this. All right. So the takeaway to all of today. Why have I taken 45 minutes to make this video for you today and put all this together? Well, it gets down to the challenge question at the very end there. The challenge question is, you have $1 million in your bank account. It's growing at a rate of 10% every year. You take out $100,000 every single year. How long does it take till you run out of money? Well, if your money's not growing, it's going to run out in 10 years. $1 million divided by 100,000, it's going to run out in 10 years. But if you notice in the question, it says it's growing by 10%. Well, how much are you taking out every year? You're taking out $100,000. You're taking out 10% per year. So that amount of money will never change. As long as you're getting 10% growth, you can take out $100,000 forever. So why do I teach this? Because if you can get to here in your life, to where you can save $1 million and hit retirement, you can live however you want. And that's what I wish for each of you. That whatever it is you want to do in life, whatever potential it is that you think that you want to hit, I want to help you get there. Learning this exponential growth is one of the most important lessons that I can teach you. If you have watched this video and not gone through the worksheet, I highly recommend you go back and give it a shot. Take some time, reflect on this, think about this. If you have any questions, please feel free to email me. I'd be happy to answer any of them. As always, I'm honored to get to teach you guys. I love what I get to do. Hopefully all of you will be back in the classroom soon. Take care of yourselves, stay safe, stay out of trouble, have fun. I'll see you guys later.